Welcome to clickmyproject.com. Let me discuss about the process self-deployment of randomly scattered mobile sensors to achieve barrier coverage. Let me discuss about the abstract of the project. Barrier coverage in a sensor network has the goal of ensuring that all paths through the surveillance domain joining points in some start region S to some target region T will intersect the coverage region associated with at least one sensor. Barrier coverage is a critical issue in wireless sensor networks for security applications, which aims to detect intruders attempting to penetrate protected areas. However, it is difficult to achieve desired barrier coverage after initial random deployment of sensors because their locations cannot be controlled or predicted. In proposed system, two deployment schemes are proposed, where sensors are deployed mobile sensor nodes over a rectangular belt to achieve sensor barrier coverage. Sensor deployment strategies have direct impact on barrier coverage. Placing sensors side by side regularly along straight lines across the region is the best one would hope to achieve, for it is simple and offers the most efficient possible barrier coverage. But it is infeasible to achieve in most applications when deploying sensors to monitor boundaries of battlefields, country borders with complex terrains, or other hard to reach areas. We may have to rely on other deployment methods. These methods may include dropping a large number of sensors from vehicles such as aircrafts along predetermined routes. Path coverage is defined and efficient algorithms are proposed to find the maximum breach path between two endpoints that are least or most likely to be detected by sensors. The notion of path exposure is introduced to measure the likelihood that an intruder is detected when moving along a given path. A centralized algorithm is proposed to find minimum exposure paths where the probability of an intruder being detected is minimized. Let me discuss about the flow diagram for our process. Initially, the random deployment within rectangular belt, that is in mobile sensor nodes, are deployed with sensing radius RS and communication range RC. Initially, sensor nodes are deployed in a rectangular belt. Binary model is designed for probability of barrier coverage estimation and construct a graph based on the vertices and edges set of the sensor nodes. Based on the equivalent distance between available nodes formed the edges. Nodes which are presented in left and right boundary of rectangular belt is called virtual nodes and that are added to reconstruct the graph. Probability of barrier coverage using depth first search algorithm has been expressed, and in the virtual force based barrier coverage algorithm has been proposed. A fully distributed algorithm based on virtual force is devised, which cooperatively controls the sensor to move approaching the optimal distribution pattern. Performance evaluation verifies the validity of the algorithm and analyzes the properties such as formation, duration, and energy cost. All the virtual physics approaches for self-deployment are similar with the framework of virtual force, which combines the ideas of potential field with circle packing by modeling the sensor node to a particle in the potential field. And in this paper, the algorithm is defined as low virtual force algorithm. On the other hand, in mobile sensor networks with large value of stacking problem caused by non-planar connectivity, graph is quite obvious. And after estimating the total force, we can go for the probability of barrier coverage estimation. And the next scheme is called the Urquhart graph or RNG and potential field theory based barrier coverage. The relative neighborhood graph is an undirected graph defined on a set of points in the equivalent plane by connecting two points P and Q by an edge whenever there does not exist a third point or it is closer to both P and Q than they are to each other. And in the Cohort graph, the graph formed by removing the longest edge from every triangle in the preliminary triangulation, was originally proposed as a fast method to compute the relative neighborhood graph. And the barrier coverage probability estimations are analyzed. Finally, the iteration has been increased. Finally, we achieve the barrier coverage, and by varying the length of rectangular belt, estimated the barrier coverage probability, compared the proposed system with existing system, such as line-based normal random offset distribution with different values of sigmas are plotted. Let me discuss about the running procedure for our process. Select the main .temp in the control and run for executing this process. Here we perform the self-deployment of our barrier coverage probability and we obtain the result. This is the initial sensor position for scenario 1. Here within the rectangular belt we deploy the sensors at a random location, and this is the final sensor position. After performing the scenario 1 scheme, we obtain the final sensor position within the rectangular field, and this is the initial sensor x coordinate and y coordinate and final sensor position x and y coordinates values, and this is the initial sensor position for scenario 2. Here the sensors are grouped into one location and formed into a rectangular belt within the rectangular belt, and this is the final sensor position for scenario 2. By performing the scenario 2 operation, we obtain the sensor positions, and this is the sensor position for scenario 2 and initial sensor x coordinate, y coordinate, and final sensor x coordinate and y coordinate values, and this is the initial sensor position for scheme 2, that is orange graph. Here the sensors are grouped at the end of the rectangular belt, that is rightmost corner of the rectangular belt, and this is the final sensor position for scheme 2. After performing the scheme 2 operation, we obtain the final sensor positions, and these are the values of the initial sensor x and y coordinate, final sensor x and y coordinates for our scheme 2 operations, and this is the barrier coverage probability of barrier coverage for various belt lengths. We obtain the results, and here we compare the existing methods, that is LNRO algorithm, for various alpha values and our scheme 1 and scheme 2 algorithm, and this is the barrier coverage probability values for our existing and our proposed algorithm. So finally we analyze the self-deployment scheme and perform the probability barrier coverage for various algorithms. Thank you.